Hey physics friends, and welcome to 3.4. I've entitled 3.4 Free Fall because we're going to be talking about just simply dropping objects, throwing objects up, throwing objects down on planet Earth. And something really unique about things that drop on planet Earth is that they all fall at the same rate. Now that might make you think, because Mr. Hare, I've dropped a tissue paper and I see leaves, and if I drop a bowling ball, the bowling ball is going to hit the ground, but the tissue paper is going to not fall at the same rate. I'm telling you that if we were to take air resistance out of the equation, that would happen. And I'm going to show you a few examples of that happening. I'll show you some cool examples of people towards Earth. We're going to do a couple of example problems, and that's going to be it. So I want to get started, first of all, with a man named Galileo. He was the first person to make an observation that it doesn't matter. He dropped a musket shot and a cannonball from the Leaning Tower of Pisa and noticed that they fell at the same rate. So he's the first person to really quantize acceleration due to gravity. And it turns out that on planet Earth, things fall at 9.8 meters per second. Meaning this, that if you were to drop something, if it's initially at rest, 1 second later, it's going 9.8 meters per second. 1 second after that, it's going twice that, so it's going 19.6 meters per second. After 3 seconds, it's going another 9.8 meters per second faster, which is going to be 29.4 meters per second. So every second that ticks by, it just gets going faster and faster and faster and faster. But in real life, because we have air resistance impedes that acceleration, and we reach what's called terminal velocity. Things end up going a certain constant velocity, and the acceleration goes to zero because it's no longer accelerating. So I want to show you a few really cool videos. Back in the 60s and 70s, in the Apollo era, one of the Apollo astronauts actually took a hammer and a feather up to the moon with him to show that in the presence of no air, when we drop things, watch what happens.
I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
Did you see that? Now, it actually goes a little bit slower than on planet. If you dropped a hammer on Earth at the same time that he dropped it here, you'd see that because he's on the moon, gravity's 1/6 of the amount of Earth's. So you'll see these things actually accelerating not at 9.8, but at the moon's gravity, but they still hit the ground at the same time because there's no air. Now, it turns out on planet Earth, I told you that the acceleration of gravity is 9.80, and that's true. All over planet Earth, it's 9.80 meters per second. But that third decimal point, it depends what you're on top of, because if you stand above a lot of rock, it's more dense, there's more gravitational attraction, and it actually accelerates more. If you're above water or something that's less dense, it doesn't attract you as hard. So actually, this is a map of Earth's gravity at different locations, with yellow being a lot of gravity, dark blue being a little bit of gravity, and you saw that it wasn't quite uniform. This is a really cool video I wanted to show you. An English scientist named Brian Cox traveled to the United States, to Cleveland, Ohio, to drop a bowling ball and a feather on planet Earth in air, and then he pumps all of the air out of this huge building and then drops it again. It turns out this building is from NASA. It's a building that I had the privilege of visiting a few years ago. Going inside, they were testing out the next generation of space. I forget what it's called, the Orion space capsule inside of here when we were there. Really cool. So I want you to, he gets into the newer physics, and that's what makes Einstein so revolutionary, is because of the way he visualized gravity and space and time, and they're intermingled. We can talk about that another day. One of the fun things that we get a chance to do every year, hopefully as you're watching this, we still do it, is we go to Great America, and there's a really great ride at Great America called the Giant Drop. So some of the students and I, a few years ago, we did a little experiment on the Giant Drop where we were taking data. There it is.
Come on, let's get pumped up. Woo! Let's go. Drop me.
I love being in free fall. It's one of my favorite things to be in.
Yeah! Woo! We got good data.
Zero gravity, apparent gravity, accelerating down at 9.8 meters per second. There's a really great video of a man who jumped from space. His name is Felix Baumgartner. It's really cool. This happened back, I forget what year, probably 4 years ago. They put him in a balloon, and he went up to, I think, 20 miles above the Earth's surface in a balloon going up there. And it's neat because when you watch this balloon, you're like, well, they didn't pump the balloon all the way up. It turns out as they get higher and higher in the sky, the pressure on that balloon that's squeezing it isn't as big. So the higher they go, the less pressure that there is. And you'll watch this balloon, when he gets up there, it's actually pretty fully inflated. And that's how they launch weather balloons in that whole thing. You can see it larger right there. And it was said that when he jumped, there's actually no air resistance, and he's so high up there that when you're falling from that height, you can't feel anything. There's no rushing of air going past you. It's just you're accelerating towards Earth, and as you enter Earth's atmosphere, you start to feel here as the air gets thicker and thicker and thicker. So this guy set the Guinness Book of World Record for tallest free flight. I think it was broken not even a year later by one of the executives at Google. But let's talk a little bit more specifically about how to solve problems involving free fall. So I've got an example problem here. It says a construction worker accidentally drops a brick from a high scaffold. What's the velocity of the brick after 4 seconds? So what you're going to do when you drop something, dropping something insinuates that the initial velocity is 0.0. So here's my construction worker. Here's my brick. What I'm going to do, I'm going to say that positive is down. So that way, because this thing is accelerating in this direction, and if it's accelerating in the positive direction, the acceleration is going to be positive. So what's the velocity? So what's my velocity after 4 seconds? Now, there's two ways to do this problem. You can kind of like logic your way through this and say, okay, after 1 second, you're going 9.8. After 2 seconds, you're going 19.6. After 3 seconds, you're going 29.4. After 4 seconds, that's 39.2, I think is what it ends up being, just off the top of my head trying to do the math. Or you can plug it into an equation. VF equals VI plus AT. VF unknown, VI is 0, acceleration is 9.80, and the time comes out to be 4. So you multiply those things, and you end up with 39 meters per second using significant figure. Now you'll notice that this is positive, which means it's traveling in this direction, and that makes sense. It's in the positive direction. And part B says how far does the brick fall? So now you're looking for the displacement. So what you could do is pick another equation. Displacement equals VI t plus 1/2 AT squared. The initial velocity is 0, so it just kills that term. 1/2 9.8 times the time, which is 4, squared. So you take 4 times 4, which is 16. Divide that by 2 is 8. 8 times 9.8 turns out to be 78. Next question. A tennis ball is thrown straight up. So here's my person. I'll tell you this. Every single physics student who draws a picture always does better than physics students who don't draw pictures. This is a documented fact that researchers have studied within physics classes. I really encourage you, in fact, I mandate that you draw pictures. I want you to do sketches. It's fun to draw pictures. Throwing my ball up there, it goes up, then it starts to fall back down. So, the first thing I'm going to do is define up as positive. I want up to be positive. So it says I'm throwing it up with the speed of this. So my initial velocity is 22.5, and that's positive because I said I'm throwing it up. It's accelerating down, which means the acceleration is negative. It's slowing down. And you can use 9.80 inside of all these accelerations to give you three significant figures. How high displacement equals question mark. Son of a gun. If you want to know how high it is, there's one thing that you can do. There's a rabbit here that they're not telling you about. And that is that the final velocity at the top is 0. It stops momentarily up there. So you can leverage that fact to then plug it into this equation. VF squared equals VI squared plus 2AD. Final velocity, initial velocity, acceleration. Make sure you put negative. If you don't, the math comes out funny. Because when you move the 22.5 squared over here, it becomes negative. And then when you divide it by a negative, then you get a positive number, and that comes out to be 25.8 meters. Just skipping over the calculation. I did it prior to this, so I know. But I could pull my calculator out and do it. Part B says, how long does it remain in the air? So now what you can do is you can find the time. So I think that I'll just use VF equals VI plus AT. Now be careful. If you use the final velocity of 0, that's the time that it's right here at the top. So when you find the time, it's going to be the time all the way to the top. You then have to double that to find how much time it's in the air. So my initial velocity of 22.5 and the acceleration of negative 9.8. So you see how that comes over here and you get negative 22.5 equals negative 9.8 t. And then my time, when I do that, turns out to be 2.3, a positive. So then I double it, and so my total time is 4.6 seconds. Here's another really cool way to do this problem. When this ball lands, it's actually going at the same speed at which it was thrown. So what I could do is say the final velocity is negative 22.5. The initial velocity is 22.5. The acceleration, negative 9.8 t. So then I subtract this, I get negative 45 equals negative 9.8 t. So my time turns out to be 4.6. And it's funny because it's exactly the same as that. So there's lots of ways to do these physics problems. Another way to do this exact same problem is to say, oh, the displacement is 0. So you pick another equation with the displacement equal to 0 and then find the time, and that will also tell you the time it took you to do it. So there's lots of cool ways to do these problems if you pick the right numbers. And then lastly, I wanted to show you one where a construction worker throws something up in the air. So here's your construction worker again. They're throwing something up. It goes up, stops, and then it goes down. And it's telling me that this construction worker is 153 meters up. So what I'm going to do, I'm going to say that up is positive. Let's see. my initial velocity is 23.0 meters per second. The acceleration is negative 9.80. That's what it always is when you throw something up in the air. The displacement, it's here, it ends here, and it starts here. The displacement is negative 153. It's negative because it starts up here and it ends down there. And then I can figure out the time. How long? This is tricky right here. The fact that that's negative, you can do that. And that's actually good because that's the displacement at the very end. And this will tell me how much time it takes to go through the whole thing. You could